This video is the 11th video in the complex number set of videos. In particular, this video is focusing on quadratic equations with complex roots. A quadratic equation is an equation where we have ax squared plus bx plus c. We've seen them many times before in algebra, you've seen them in functions, and the main thing is here, a, b and c are real numbers. The solutions can be found using the quadratic formula or the minus b formula that is on the front of your formula and tables booklet. B squared minus 4ac is called the discriminant. That's the part that's underneath the square root. Now, if the discriminant is 0 or positive, the solutions are real. However, if the discriminant is negative, there are no real solutions. Instead, the solutions are complex. Before studying complex numbers, when you would have got a negative underneath the square root, or if you were typing the quadratic formula into your calculator and you got an error, you knew that you'd completed the question incorrectly, as the quadratic could not be equal to 0. However, now we write the square root of a negative number by introducing the imaginary unit I, as we have before, where I is equal to the square root of minus 1. Now, unlike before, if we got an error on our calculator or a negative number underneath the square root, we can solve it. We find the square root of the positive number b squared minus 4ac, whatever that is, and then we take the square root of minus 1 and replace that with I. Therefore, as I say here, thus, if b squared minus 4ac is less than 0, we express the square root of b squared minus 4ac as the square root of minus d, where d is equal to b squared minus 4ac, and we can then get the square root of d and replace the square root of minus 1 as I. When you are solving a quadratic equation in which b squared minus 4ac is less than 0, and you change it into a complex number, then the two answers, or the two solutions, or the two roots that you find will be conjugates of each other, meaning that they have the same real part and opposite imaginary part. This is best explained by going through an example. Example 11.1 says solve z squared plus 2z plus 10 is equal to 0 and express the answer in the form x plus yi. This quadratic equation is in the form a z squared plus bz plus c is equal to 0. As it's in this form, we know what a, what b, and what c are going to be. A is 1, the number in front of z squared, b is the number in front of z, which is 2, and c is the number by itself, which is 10. Filling this into the quadratic equation, well, z will be equal to minus b plus or minus the square root of b squared minus 4ac, and that will all be over 2a. I will have minus 2 plus or minus the square root of 2 squared minus 4 times 1 times 10. And that's all over 2 times 1. Simplifying that down then, I'll have minus 2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 10, which is 40. And that's all over 2. Again, I'm going to simplify that down, and I'm just going to give myself a bit more space up here, and I'll get that z is equal to minus 2 plus or minus the square root of minus 36 all over 2. Here we have a negative underneath the square root, meaning that we need to change it into an imaginary number. This will be z is equal to minus 2 plus or minus the square root of 36 multiplied by the square root of minus 1 all over 2. Finally then, removing the square roots, we get minus 2 plus or minus 6i all over 2. This will simplify then to minus 2 over 2 plus or minus 6i over 2, which will simplify again to minus 1 plus or minus 3i. We have two answers for this. We have minus 1 plus 3i and minus 1 minus 3i. Therefore, it's asked us to solve z squared plus 2z plus 10 is equal to 0 and express the answer in the form x plus yi. Here we have two answers. We have minus 1 plus 3i, minus 1 minus 3i. Minus 1 plus 3 and minus 1 minus 3i are conjugates of each other, as the real numbers are the same. We have -1 and -1, but the imaginary parts are different. We have +3i and -3i. In example 11.2, it says solve the equation z squared minus 8z plus 25 is equal to 0 and express your answer in the form a plus bi. Similar to the last question, we've been given a quadratic equation and asked to solve it and express our answers in the form a plus bi. Here, the fact that it says a plus bi means that it's going to have complex roots, meaning that b squared minus 4ac will be less than 0. Writing out the quadratic equation, we have z squared minus 8z plus 25 is equal to 0. That matches up with the quadratic equation az squared plus bz plus c is equal to 0. Moving on from there then, I'm able to label my a, my b and my c. A will be 1, b will be -8 and c will be 25. Writing down the quadratic formula, we have that z is going to be equal to minus b plus or minus the square root of b squared minus 4ac, and that's all over 2a. Filling that in, we'll get that z is equal to 8 plus or minus the square root of -8 squared minus 4 times 1 times 25. That's all over 2 times 1. Breaking that down again, we'll get that z is equal to 8 plus or minus the square root of -8 squared. 8 times 8 is 64. Minus 4 times 1 times 25, which is -100. All of that then is over 2. Simplifying it again, we have 8 plus or minus the square root of 64 minus 100, which gives us -36 all over 2. Like the last time, I'm going to change the -36 into an imaginary number. I'll end up with z is equal to 8 plus or minus the square root of 36 multiplied by the square root of -1, and that's all over 2. The square root of 36 will give us 6, and the square root of -1 is I, and that's all over 2. Breaking that down then, we'll have 8 over 2 plus or minus 6i over 2. That will leave us with 4 plus or minus 3i. And again, we can write that z is equal to 4 plus 3i, z is equal to 4 minus 3i. Another type of question they can ask you to do with a complex number and a quadratic equation is to verify that a complex number is a root of the quadratic equation. When asked to do that, all you have to do is substitute the complex number into the equation and simplify the result. If the simplified expression equals 0, then the complex number is indeed a root. In example 11.3, it says show that -3 plus I is a root of the equation z squared plus 6z plus 10 is equal to 0 and find the other root. Here I will replace z with -3 plus I, simplify the left hand side, and once it's simplified, if the left hand side is equal to the right hand side, which is 0, we will know that -3 plus I is a root of the quadratic equation. First, we have z squared, which is -3 plus I squared, plus 6 times -3 plus I, plus 10 is equal to 0. -3 plus I squared is -3 plus I times -3 plus I. I'll multiply out the bracket and I'll have 6 times -3 and 6 times I, meaning I'll be left with -18 plus 6i plus 10 is equal to 0. Multiplying out the brackets, I'll have -3 times -3, -3 times I times -3, and I times I. That will leave me with 9, -3i, -3i plus I squared, -18 plus 6i plus 10. Underlining like terms, will I have 9, -18 and plus 10. I have minus 3i minus 3i and plus 6i, and I have I squared. I know that I squared is equal to minus 1, so I'll replace the I squared with minus 1. I have minus 3i, which is minus 6i, and then plus 6i, that will give us 0. And then I have 9 minus 18 plus 10. 9 minus 18 is minus 9, plus 10 is 1. So I'll be left with 1 minus 1 is equal to 0. Therefore, 0 is equal to 0. So yes, minus 3 plus I is a root. Now, the next thing it says, and find the other root. If you can remember, even looking back up at example 11.2, when we have the solution of a quadratic equation in which we need complex roots, if the first root is 4 plus 3i, the second root will be the conjugate of that, 4 minus 3i. Therefore, if we look down here, if we have minus 3 plus I as a root, well then the other root we're going to have is minus 3 minus I. To remind you about this, if we have a root of a quadratic equation and that root is complex, well then another root of that quadratic equation will be that complex number but its conjugate. The conjugate again is where we change the sign of the imaginary part of a complex number while leaving the real part exactly the same. That means that minus 3 plus I and minus 3 minus I are both roots of the equation z squared plus 6z plus 10 is equal to 0. Example 11.4 says show that the root minus 2 minus 4i is a root of the equation z squared plus 4z plus 20 is equal to 0, and write down the other root. This example is very similar to the last example, so we do it in the exact same way. We sub in the complex number minus 2 minus 4i into the equation. If the left-hand side is equal to the right-hand side, we know that it is a root of the equation, and the conjugate will be the other root of the equation. Subbing in, we get minus 2 minus 4i squared plus 4 times minus 2 minus 4i plus 20 is equal to 0. Minus 2 minus 4i squared is the same as minus 2 minus 4i times minus 2 minus 4i. Multiplying in the 4 here to the minus 2 and the minus 4i, we will get minus 8 minus 16i and plus 20 is equal to 0. Multiplying out the bracket then here, we'll have minus 2 times minus 2, minus 2 times minus 4, minus 4i times minus 2, minus 4i times minus 4i. Minus 2 times minus 2 will be 4. Minus 2 times minus 4i is plus 8i. Minus 4i times minus 2i is plus 8i. And minus 4i times minus 4i is plus 16i squared. Then we will have minus 8i minus 16i plus 20 is equal to 0. Highlighting the like terms, first of all, we have 4 minus 8 plus 20. We have plus 8i minus 16i and plus 16i squared. Here we know that I squared is minus 1, so we will replace the I squared with minus 1. Next, plus 8i is 16i, and minus 16i will give us 0i, so the i's cancel out. We'll then have 4 minus 8, which is minus 4, plus 20, which will give us 16. Meaning we'll end up with 16 plus 16 times minus 1. That is equal to 0, and we will end up with 16 minus 16 is equal to 0. Therefore, 0 is equal to 0, which is correct, meaning that minus 2 minus 4i satisfies the equation, meaning that minus 2 minus 4i is a root. The conjugate then will also be a root, meaning that minus 2 plus 4i is also a root. We've now finished that question. It said show that -2 minus 4i is a root of the equation and write down the other root. We have shown that the left hand side is equal to the right hand side when you sub in the root, which is -2 minus 4i, and then another root is always going to be the conjugate. If a complex number is given as a root of a quadratic equation, you can substitute it into the equation to determine any unknown coefficients. This is best explained or explained further by looking at an example. In example 11.5, it says if -6 minus I is a root of z squared plus az plus b, find a and b. First of all, I'm going to sub in -6 minus I into the equation. That will give me -6 minus I squared plus a times -6 minus I plus b is equal to 0. -6 minus I squared is -6 minus I times -6 minus I. We'll then have a times -6 and a times -1, leaving us with -6a minus ai plus b is equal to 0. On the next line, I'm going to multiply out the brackets. We have -6 times -6, -6 times I times -6, and -I times -I. Here we have -6 times -6, which will give us 36. -6 times -I, which is plus 6i. -I times -6, which is plus 6i. And finally, -I times -I, which will give us plus I squared. Then we'll have -6a minus ai plus b is equal to 0. Next, I can see I have an I squared here. I'm going to replace that with -1, meaning I'll be left with -1 there instead of the I squared. I'm going to highlight my like terms. I first of all have 36. -1 is a number. -6a is a number as there's no I there. And plus b is a number as there's no I there. The 6i and the 6i and the -ai are also like terms as they are all I. Bring it back then and up here just to give me a bit more space. I have 36 -1 minus 6a plus b is equal to 0. They're all the numbers and they have to all be equal to 0. Similarly, I have 6i plus 6i minus ai, and they have to all be equal to 0. Adding those two together, we will get 12i minus ai will be equal to 0. Minusing the 12i from both sides, I'll end up with minus ai is equal to minus 12i. I'm going to divide everything by minus I, meaning I'll be left with a equal to plus 12. Now that we know that a is 12, I can replace the a in the top line with 12. First of all, we have 36 minus 1, so we'll get 35. Minus 6 times 12 plus b is equal to 0. I then have 35 minus 6 times 12. So 6 times 12, we will get 72. So it will be 35 minus 72 plus b is equal to 0. 35 minus 72 will give us minus 37. So we'll get b is equal to 37. We figured out that a is 12 and b is 37, as in the question it said -6 minus I is a root of the quadratic equation z squared plus az plus b is equal to 0. On the next page, example 11.6 is the exact same. All you'll need to do is sub in the root that they've given you and equate the real numbers and the imaginary numbers and solve to find what the two values are. That brings this video to a close, which is all about solving quadratic equations with complex roots.